Okay, class. So today I'm going to be going over some of the homework and starting some of it for you guys. So first off, in problem number 1, we have a ceiling here. We have our coordinate axes, y and x, and we have a 2-pulley system here. And we have a person, and attached to this second pulley here is a mass M. So first we want to draw a free body diagram. So here there's going to be a tension here, which that is equal to the tension here, and then we have the normal force here. So going in the upwards direction, we have 2T here, and then downwards we have mg. Let's wait. Simple enough, because we have a T here, and this T is the same there. So for writing the net force here, we just have the sum of the y components. So sum of F net equals sum for Fy, which is equal to 2T minus mg. And so then we can say that this is may is equal to 2T minus mg, and then so we can say that ay is going to be equal to 2T over m minus g. Simple enough. And so we say that the man is pulling the rope with a force F1, so that's the tension. So whatever that this man is pulling with, that's going to be the same T everywhere. And so then we say that F man is equal to T. And so then you plug in what your T is here, and then you will be able to get A. Okay, so next up we've got a basketball player here. And what they do is first they lower their body to a certain distance here, and then they increase it to, and they jump up and they increase their distance in the vertical direction. For this, we can easily solve for the initial velocity that he pushes off with via one of our kinematic equations. And so this d here is just the difference between these two, because it's delta y. So this is final minus initial, so we'll write these like that. And so then this is going to be equal to 0, because this will be the velocity at his peak, which will be 0. So in order to do this, we say that v naught is equal to negative 2a delta y. And his acceleration is going to be that negative there. So we'll just make that a positive. And so that we say that v0 is equal to 2a delta y. We just know that the negative cancels out here, because this is technically g. So now we're safe to use the square root here. So next up, we just plug in 2a and the difference between these two, where delta y is going to be equal to df minus di, and then that'll give you your velocity. And so now it's going to ask what is his acceleration as he's straightening his legs. So we're now not talking about when he's in the air, but in between these two stages here. So in this case, we can use the same equation. But in this case now, we know that VI is equal to 0. And so then we can calculate the acceleration by saying A is equal to VF squared over 2A, 2 delta Y, not 2A delta Y. And so now what we're going to have here is, in this case, the initial velocity that we solved for earlier is going to be the final velocity in this case. So then we can say that A is equal to 2A y over 2 delta y. And so this is going to be, so these are different delta y's here. So in this case, we have our 2's cancel. A is equal to G here, because they're not the same A's. So you can't cancel those out. And then this is going to be your final height here, and this is going to be the initial height that you're given. So we can erase this and say that this is going to be DI here, and you can say that this one is going to be DF. And so then you can calculate the acceleration. And so then if you are and so this will be your acceleration. So this is, I'm going to rewrite this so it's clear. This is going to be equal to G dF over DI. And now we can calculate the force that he exerts on the ground in order to get himself off, and that's just going to be F net is equal to MA, where M is his mass, and A is this, so this is going to equal mg dF over DI. And so then we can also say, next up, we can say, well, while he's in the air, we can say that F net is going to be equal to the force that he just exerted on the ground. So mg dF over DI, and then we can subtract mg, or his weight. And so now what we can do is we can now look for what F is here. Oh, no, I made a mistake. So this goes here, mg dF over DI, and then this is the force that he pushes off on the ground with. And so then we can say that F is equal to mg dF over DI plus 1. And then, so this will be your force. So next up, we got a car, and we've got, it's going to pull this boat here. I'm just going to draw that as a sail there. And so now we know the mass of the car. We're going to label that M1 or MC, M car, and then this is going to be M boat or MB. And so we say that the car exerts a certain force on the road and produces a certain acceleration. So we know what A are and we know what F is. And so we can what our job is to find the magnitude of the force which resists the motion of the car, boat, and trailer if the car exerts a force on the road and produces an acceleration. So we can say that F net here is going to equal ma, like usual, and that then F net equals m1 plus, or mc plus mb times a. And now, so we can then write a sum of the forces of the car, boat, and trailer. So we have capital F minus little f, and so then we can set these two equal to each other, mc plus mb all over a. And then so then we can solve for one of these forces, and so let's solve for little f here, and we can say that little f is equal to f minus mc plus mb a. And so then you can say that, so big F is the force we know, A is the acceleration that is given in the problem, and then the M's are the masses of the boat and the car. And so now what is part B asks, what is the force that in the hitch between the car and the trailer if 80% of the resisting forces are experienced by the boat and the trailer. Okay, so next up we have that we know that F net is still equal to M2A because we're looking at it from a different point of view. And so then F net prime is going to be equal to F prime minus 0.8 F. So we just have to tack on a 0.8 here into our equation. And we're finding F prime, which is going to be our new force here. And so now we know what F is from our earlier equation, or little f, and we set these two equal to each other, so m2a is equal to f prime minus 0.8 f, and so then we can solve for f prime. So f prime is going to be equal to m2a plus 0.8 f. But then we know what F is, so we're just going to write that as MC plus MB times A. And then you can plug in all your numbers here and solve for this force. Again, this is F prime is equal to M2A plus 0.8 times the quantity MC plus MB times A. So this is an A over here. Next up, we're cooking breakfast here, and we got some food on there. And so one thing that we know from the problem is that we have our spatula here, and we know the frictional force between our spatula, and we know that the coefficient of kinetic friction between the two is a certain number. So we know that Fk is equal to mu k n, and so then we can quickly solve this for n. So then n is equal to Fk over mu k, and so then that just gives you the normal force. So quick and easy friction problem. That's all you have to do. Quick and simple. So next we have a wooden crate resting on a wood floor. And we know that the coefficients of static friction are, we know that mu s and mu k, we know those two. So we can first off, we have to do what is the maximum force in newtons can you exert horizontally on a crate without moving it. So Fs is going to be equal to mu s n, and then this is equal to mu s mg. And so we know the mass here of this wooden box, and we know what gravity is, and we know what the coefficient of friction is. So we've easily found the maximum force that we can exert. So if you can continue to exert this force once the crate slips, what is the acceleration going to be in meters per second? We can start by writing our F net, and so here we know that this is equal to ma, and then we'll write our expression. This is going to be F max. So this is the force. We already know what force we're exerting. We're exerting the force that it took to break the coefficient of static friction. And then we can subtract the frictional force here. So this is going to be, so we solved for the force that we're going to be using in the second problem here. And so this is going to be mu of Kn, which is just equal to mg. And so then we know what F max is. This is going to be mu s. And so what we can do is we're plugging in this here, and we have a couple factors that can come out. So we have mg is equal to mu s minus mu k, because we just factored out the mg here. Quick and simple. We know that this is still equal to ma, so then we know that the acceleration is going to be equal to g mu s minus mu k. Okay, so next thing up, we have half the weight of a small utility truck is supported by its two drive wheels. Assume the coefficient of static and kinetic friction are certain numbers. So in this case, we have when we have a tire on a road here, the tire, from the point of the tire, it never, I don't know how to exactly explain this, but it moves like this. And so what we can say is that the static friction is scuffed. Okay, hello. So the next question that we have suppose the weight of a small utility truck is supported by its two drive wheels. Assume that the coefficient of static and kinetic friction are certain variables. So one thing that we can say is that the tire doesn't actually move along the road, so it's just, all it is it's rolling. So the point of contact is just is going to be the same down here. So technically it's not rolling, or it is rolling, but it's not actually sliding. So our coefficients of friction are meant for sliding friction. This is not sliding friction. This thing is rolling. So that static friction is making this tire constantly change its point of contact around as that point of contact touches the ground. So we're trying to find the magnitude of maximum acceleration it can achieve on dry concrete. So we want to find what F max is, which is going to be just F of static friction. So then we have mu s times the normal force n. So this is going to be mu s mg. And so then all we have to do is to find the maximum acceleration. We must now divide the maximum force by the mass of the truck. And so now in this case, we saw that in this case, half of the mass was being supported by its drive wheels. And so then we have to add in a 0.5 in here. because the weight is only being, half the weight is being supported by the drive wheels. And so then this is going to be equal to MA and so then A is going to equal 0.5 mu s g. And so next up, we want to find the magnitude of maximum acceleration it can achieve on dry concrete in meters per second, assuming the truck has four-wheel drive. So now all the wheels are now drive wheels. And so now the only thing that changes here is that we can get rid of this 0.5 here. And so now the derivation is exactly the same, but we just arrive at our new solution without the 0.5. Okay, so next up we have a block here, and there are two forces being exerted on it, one from this side and one coming down from this side at some angle theta. And the surface is not frictionless, so we know we have a mu of k here. And so we have F1 has a value, and we are given the value of F2, and we are given the mass of the block. And so the first part asks you solve numerically for the magnitude of the normal force in newtons that acts on the block if theta is equal to 30 degrees. So this is F2, this is F1. And so now what we have to do is we know that W acts here, and this is equal to mg. But we have to subtract off some of the force, or we have to add on some of the force actually, because the force here is going to increase the downward force here. And so now if we break this into its components, this is Fy, this is Fx. And so then we have that F net x is going to be equal to mg plus Fy. And now Fy is going to be the opposite, so we're going to use sine there. So sine of theta is equal to Fy over F. And so then we can plug Fy in here. And so then Fy is going to be F sine theta. And so then this is going to be equal to the normal force here. There's our normal force. So next we have to solve numerically for the magnitude of the acceleration of the block if theta is equal to 30. So then cosine of theta here is going to be equal to Fx over F. So then Fx is equal to F times cosine theta. And that's supposed to be a y. So then we have that F net x is going to be equal to F1 plus F2 plus mu of k Fn. And then this is going to be all equal to max. So a couple things that we can do right off the bat. F1 is all in the horizontal, and so then plus F2, or we can say minus F2 because it's going to be in the opposite direction. Oh, one thing we should do first is we should compare the F1 and F2. So in my problem, I'm given that F1 is far larger than F2, so any value of cosine theta is not going to make F2 larger than F1. So there's no fussing about here. So we know that F1 is going to be greater than F2. So we know the block is going to move in that direction just by a analysis. So we know that AX is going to be in that direction. So we know that F2 is going to be subtracted here, and so is mu of K. Fn is going to be equal to mg plus F2 sine theta. And we also have to plug in what F2 is here. So in this case, this is going to be F2x. So then we have to substitute in what F2x is. And so then this is going to be equal to F2 cosine of theta. And so then we have to divide both sides by m. So AX is equal to all of this over m. So then you start plugging in your numbers, and that will give you A of x. Okay, next up we have a little inclined plane problem. So we have our inclined plane, we have our package, or we have our box here with a mass m. We know that our weight points downwards. We know that the force of friction is in that direction, and we know that Fn is in this direction here. So now what we have to do is we have to split the weight up into its different components. So one here and one here. I'm going to redraw these. This is theta in here. So now this is going to be a similar triangle. So this is going to be equal to theta. So this is going to be technically our y component. We don't know. We don't really need to say that it's our y component because it's not necessarily pointing downwards, but we're just using, we can twist our coordinate system in any which way we want here. We can say that this is y and this is x. And, or even if you wanted to, you could say this is x. It doesn't matter. We can define our coordinate system in any which way we want. So, but we do know a couple things about our trig identities. We know that Fy over W is going to be equal to cosine theta, and that sine theta is going to be equal to Fx over W. We're going to be using these trig identities basically all year, so I hope you guys have gotten used to them at this point. So Fn is just going to be equal to Fy in this case. And so then F of friction is going to be equal to mu. I'm going to put that as an I because it can either be static or kinetic friction based on what we need the problem to do. Fn, which is going to be equal to Fy. So this is going to be W cosine theta. So now we know what friction is. We know what Fn is because Fn, I'll just write it out explicitly, is equal to Fy, which is equal to W cosine theta. And so first problem, you have to draw your free body diagram. We've done that here. So next up, we have to do input. We have to find an expression for the net force. So now you just have to sum up F and X. We know what Fx is. We know what F friction is. So you guys just need to put in your your equations there. So if I derive these equations for you, this will be giving you the answers because there are no numbers. So go through. We've already set this problem up, but I'm going to move on from here. You guys should have all the tools to solve this problem. Okay, so next up we have a mass dangling over a table that is attached to a mass on the table, and the table is flat. So let's write that. Here we go. We have this. We have M1. We have a pulley. And we have M2. And so we know what mu of k is. It's given in the problem. And we know what the two masses are, M1 and M2. So these are knowns. And so it's asking us to, using variable t to represent tension, write an expression here. So let's just draw a free body diagram. We know that for M2, this is equal to T, and then there's a W on it. And we know that W2 is equal to M2G. And so then you just have to sum these forces up. And so now we have to do the same thing, but for the other block. So we just have this block here. We have W1 is equal to M1G. We have the normal force here. And then here we have T. And then on this side we have friction. And so you just need to sum these forces up and have and write an expression for f of x. So you just have to sum the tension and the frictional forces, but you get the frictional force from the normal force, which you get from the weight. Easy peasy. So next up, we are writing an expression for the acceleration of block 2 in terms of block 1. Just remember that they're connected here. So if they're connected, that should say something about their accelerations with respect to each other. So then we have to write an expression of for t. So we have from the first couple parts of the problem, you have what f of x was, or f net x. You have f net y. For both of these, you should be able to derive the expression t from either one of those two. And so then you'll have a system of equations that you can solve, and then once you get to that expression t, you just have to plug in numbers for the last part of the problem. So next we have a car driving on a circular track. And so here's our car here. We're looking at it from above. That's why we don't see any wheels. So the car is driving along a circular track of that has some diameter, and we're drawing our diameter from the center of the track on each side. So not the actual outer diameter or inner diameter. We're doing it midway, and we're assuming that the car drives along this line here. And we're given what V is. And so real quick, we can say that R is equal to 2D. And so then we can say that this is D over 2, excuse me. And so from here, we can say that A is equal to V2 or V squared over R, which then we can say is equal to V squared over D over 2, which then gives us 2V squared over D. And then so from here you can just plug in variables, and that will give you your acceleration. And so then we have to write an expression for the minimum coefficient of friction, mu, between the car's tires and the road that is required in order for to keep the car going in a circle in terms of the given parameters. So a couple things that we have to note. The car is going to have a weight that's going to be into the page here. So we're going to say x. We're going to write an x there. And so then x is going to be equal to our weight, which is going to be mg. And so then if we have a dot out of the page, so then dot is going to be equal to normal force, which is going to be equal to the weight here in the opposite direction. And so then we're going to have a force of friction pulling that way because the radial force here is pointing inwards because our A here points inwards. So I'm going to say FR and AR there. And so then this is F friction. And so now in this case, these F's are going to have to be equal to each other. And so then what we have to do is we're finding this coefficient of friction, correct? So in this case, we have to say that we have to find out what FC is first. So then this is FC is just going to be equal to MA, which is going to be equal to 2mv squared over d. And force of friction is just going to be mu. And this, we're looking for the minimum coefficient of friction so that it stays on the track. Mu n, which is going to be equal to mg. So these two have to be equal to each other for it to stay in the middle, because we have that. If we just want to stop in time and say that this is f of x, we can say that we have to have these two equal to 0 so that it stays on the center of the track. So then if these two are in opposite directions, you would be subtracting them in the F net when you're finding what F net is. So then they have to be equal to each other for it to not move in the x direction. So you just have to set these equal to each other. So then we see that the mass cancels, and then we would divide this equation here by g, and then you would get that mu min is equal to 2v squared over gd. And so and then you just have to plug in numbers for the next part. Okay, so next up, we have two blocks, and they're going to be on a turntable here, or at least one of them is. So this is going to be M1 here, and then below this we're going to have our second mass here, M2. And so then this is moving in that direction and has a V at every point parallel to or perpendicular to the string with V. And so we are given R, we're given M1 and M2 here in this problem. We know that A is equal to VT squared over R, and we're given what or we're looking for what V is here. And so we know that in this case, we have to have that FC is going to equal FT. And so then this is going to equal mVT squared over R, which is going to equal mg, because t in this case is going to point inwards, and then t here is going to be outwards, and then you're going to have an mg here. So then t here is going to be equal to mg, and so then t equals t, so then t equals mg. So then masses cancel, so then vt is equal to the square root of gr. Oh, never mind, the masses don't cancel, they're different masses. Excuse me. So this is m1, this is m2. And so then this becomes a ratio of m2g times r over m1. And so then we say how much time in seconds does it take for the block to do one revolution. So we can say that v is equal to omega r here. So then we just have to find omega, which is v over r. And we know that omega is also equal to 2 pi over the period t here. And so then we just have to solve for what t is. So then t is going to be equal to 2 pi r, which is our circumference, so that's good, over v. So distance it takes to travel over the velocity. And so this is yielding a pretty good equation here. So then we just have to plug in what vt is. So then t is equal to 2 pi r all over square root of m2g over r over m1. And so then you just plug in numbers there. Okay, so we have a similar problem here with the turntable and our masses, m1, m2. So we want to know find the speed of the circular motion at which block 1 begins to slip outward along the surface of the turntable. Enter your answer in meters per second squared. Okay, so next up, come on, don't do this to me. Okay, so we can say that Fc is equal to our force of friction plus our force of tension here. So this is m1 v squared over r, and then this is going to be u of s m1g plus m2g. And so then we just need to solve for v. So then v squared is going to equal, or we're just going to do the square root all at once. So then we're going to have mu s, and we're going to say that this is just mu sg times r plus m2g r over m1. So I've canceled out the m1s here from both sides and taken the square root, multiplied the r to the other side. So lickety split, we've found what our velocity is here. It's quite similar to the other problem. You just got to draw your free body diagrams, and those should pop out pretty quickly. So now we're talking about the gravitron, everybody's favorite carnival ride here. Unless you get motion sickness, then it's your least favorite. So we have a cylinder here, right? Height h, r, and so we stand people up against the wall and it starts to rotate. So it's got some omega here. And so we have to find the minimum speed in meters per second that the cylinder must make to ensure a person is going to stick to the wall. So at a certain point, the floor is going to be lowered, and so we're going to have people stuck to the wall here. And so we need to make sure that they just stay there because we're taking out the floor here. So in this case, we have, I'm going to erase this and draw the person here. They're going to have weight here, where W is going to be equal to mg. And so we need to make sure that this person sticks here, right? And so then Fn is going to be pointed in this direction. And in this case, F is going to be pointed upwards here. So we have to make sure that F friction is going to be equal to F force of gravity, which is just equal to W. So mg. So then in this case, Fn in this case is going to be equal to mu of s. And then the normal force here is just going to be our radial force here, or our centrifugal force. So then this is going to be Vt squared over r. And so then this is going to be the minimum velocity that we need to spin this up, or to make sure this person doesn't slip. So then we have mgr over mu s, and then we just need to take the square root of that to get Vt min. Oh, I have left out a mass here. Masses cancel, so there's no m in here. So it's just gr times mu of s. Okay, so what is the frequency in revolutions per minute of the carnival ride when it's reached the minimum speed to stick to the wall? So we have V min is equal to omega min times r. So then omega min is going to equal V min over r. And so then we just need to plug in what these are. So this is omega min is going to equal square root of gr over mu s over r. And we have to also, we're talking about frequency here. So we have found what omega min is, but now we have to use frequency. So omega min is equal to 2 pi f. So then f is equal to omega min over 2 pi. So then f is going to be equal to square root of gr over mu s all over 2 pi r. And then you just have to plug your numbers in, and that one is solved as well. I'm going to leave the last two problems up to you guys. I feel like we've done enough examples here for you guys to get the point of what we need to be doing in this chapter. So good luck. I hope you guys get your homework done by tomorrow, and have a nice day. I'll be back later today with another video.